Welcome to the STEM Pathways podcast, where we delve into the fascinating world of science, technology, engineering, and math. I'm your host, Rohan Sharma, a passionate explorer of all things STEM. Each episode, we bring you captivating stories, cutting-edge research, and inspiring interviews with experts and enthusiasts who are pushing the boundaries of innovation. Whether you're a student, a professional, or just curious about how the world works, join us as we unlock the mysteries of the universe and explore the endless possibilities of STEM. Let's get started. Today, I'll be interviewing James O'Brien, who holds a Ph.D. from Georgia Tech and is currently a computer science professor at UC Berkeley. How are you doing today?
Doing good. How about yourself? It's nice to be here.
Yeah, thank you for joining me on the podcast. So to start off, I wanted to ask what made you choose your major of computer science in college?
Yeah, that's a great question. From a young age, I enjoyed working with computers. When I was like a kid in fourth grade, my father had a computer in the house, which today is like everybody's got a computer in the house. You've got one in your pocket right now. You probably got one in your wrist, and actually, you've got two in your ears right now. Um, but back then, it was relatively unusual. Like this was when IBM was first coming out with PCs, and Apple hadn't even released Macintosh yet. They're still doing the Apple IIe, I think was what the machine that was being used at the time was. And for whatever reason, I found it really enjoyable. It was actually through a video game. There was this kind of text-only video game, I guess, sort of one of those adventure games where it says, "Oh, you're in a forest. You go right or left, and you go down some adventure path." And what I realized was that the game was written in BASIC, and so you could press Control C and then list the code of the game. And so now, if you want to know whether you should go right or left, you could actually look at the game code and see. So technically, that's cheating at the game. But I found looking at the code and figuring out what it did and even changing it more interesting than the game itself. And that's kind of how I got started with this idea of programming. It was in BASIC back then. It was a very easy, accessible language, very easy to work with. And then I found that I liked it, and so I kept doing it. Did it through took programming classes in high school, and then when I went to undergrad, I decided that was what I would major in. And when I talk to students today, I mean, I don't think everybody should major in CS. I love CS. If you want to major in CS, awesome, that's great. But what I think students should do is, try to find the thing, there's many things that you love doing. Of those things, try to find one that you love to do, because if you don't love doing something, you're never going to be good at it. If you don't enjoy it, it's hard to, if you want to be good at something, you need to spend a lot of hours, whether it's programming, doing experiments with chemistry, experiments in the lab, writing a book, studying economics, whatever you're doing. If you don't like it, you're not going to want to spend time on it. If you don't spend time on it, you'll never be good at it. And so I think students should, when they think about what they're going to study in college, they should look for two things. One that they like, something that they enjoy, right? So that they have the opportunity to first enjoy their work, have a good time while they're studying, have a good time when they go out and get a job and do their work, so they enjoy it. But also because by enjoying it, they'll have the possibility of becoming very good at it. But there's one other piece, which is it can't just be something that you like doing and no one else cares about, right? You want to look and say, of all the things in this world that I love to do, that I find very fun and exciting, which are the ones that other people care about? Like if I do this thing, people will care about it. They'll pay me to do it, or I'll do it and I'll create something that people will buy. People care about it, right? If you find some niche thing that you love and no one else, doesn't matter to anyone else, it's a great hobby, but it'll be hard to make a living from it. And then the last piece is, if possible, if you can find something that you love to do, that people care about, and that is actually hard to do, that's a really great thing, because you like it, you'll do it, you'll focus on it, you'll put time into it, and you'll eventually become good. People will care about it because that was part of the criteria. And because it's hard, people will value what you're able to do. People, right? If it's something easy, they'll just do it for themselves. But if it's something like, for example, programming a computer, most people don't know how to do that. If you learn how to do it and you're good at it, people need computers programmed to do things, and it's hard for them to do it themselves. So that sounds like a good career path. And and it doesn't have to be program a computer. Maybe you're really great at speaking, and so you're great at taking a complicated idea and explaining it in a clear way. Maybe you should go into politics and give speeches. Maybe you should be a speechwriter for a politician, right? There's all kinds of things you can do, but I think those three pieces are really important. You have to like doing it, otherwise you're going to be miserable and never good at it. People need to care, otherwise you're just sitting in a corner by yourself. and it has to be hard. Otherwise, well, why would someone pay you to do it as opposed to doing it themselves, or paying someone else the least possible amount of money to do it?
Yeah. So, moving on from that, I wanted to ask what your experience was like while getting your bachelor's and then your PhD.
Well, it was a long period of time, so lots of different experiences. Undergraduate, I found be very enjoyable. It's a time for you to learn and explore things. I liked doing that. I liked the classes I was taking. There was certainly a lot that I learned, right? I mean, even coming into undergraduate, I thought, oh, I already know how to program. I've been programming computers for a long time, written lots of programs that do all sorts of different things. And then I realized, wow, there's a lot that I don't know. And a lot of people today are self-taught in different areas. I still think there's a big value in getting that undergraduate degree, because it puts structure into all the things that you've sort of learned here and there. It brings them together. It teaches you theory, which people sort of say, "Oh, theory, what's that good? It's theoretical. It's not useful." Well, that's not true, right? Theory gives you a context for thinking about things in a way to see the connections between things. So, if you should go to when you go to your undergrad education, you should definitely do something that's practical and useful that you enjoy doing. But don't turn your nose up at the theoretical aspects of it, right? That's actually how you really get deep into a subject and really understand it. And that's something that I found when I was an undergraduate, right? I took these classes that weren't just programming, but were the theory behind programming, things like discrete math, or computer in computer science. We have a branch called theory where you study problems. What makes something slow? What makes it fast? Why would some algorithms be really great to run on big problems, whereas other algorithms aren't? And those are the tools you get during that undergraduate education, or at least that if you study CS, you do. In other areas, you get different tools. Grad school was interesting because grad school is a chance, when you're an undergraduate, you kind of get a bit of a broadness to it, right? You take your class, whatever your major is, but you also take a composition class, and you also take a language class, right? There's all these requirements that are kind of spread out. So you get a diversity of experiences as an undergraduate. And I know that some students don't always like it. They'll say, oh, I hate my English class because I came to study, programming. Why do I have to take an English class? And I would say that really, those classes, if you don't like them, you can make them as miserable as you want. But if you kind of are open to the experience of learning something that's maybe not directly in the niche that you wanted to learn, but gain that broad base of knowledge, you'll find that it can be pretty enjoyable. And I've always been surprised how things that I learned as an undergraduate that I thought were nothing to do with anything that I would do professionally, suddenly I'm like, oh, wow, that knowledge is suddenly very useful for what I'm doing. So that breadth of experience, that breadth of knowledge you get as an undergraduate in your degree, that I'd encourage people to embrace that, because there's a lot there, right? You're taking the class anyways, you might as well get something out of it, right? And it turns out when you kind of say, okay, I'm just going to see what I get out of it, a lot of these classes that maybe wouldn't have been fun otherwise can be very enjoyable. In grad school, it's a little bit different. In grad school, you kind of, especially if you're getting a PhD, you really need to kind of focus in on your research, right? And by the time, if you get a PhD, by the time you graduate, you're probably the person in the world that knows the most about your thesis topic, right? I mean, that's kind of what you want to get to, because a good PhD thesis is something new that hasn't been done before, that hasn't been seen before, some new bit of information, some new theory, some new idea. And you get that by really, going deep into a subject. And so grad school is an opportunity to do that. We should be open, I think, to learning other things. And even when you go deep into a subject, you'll see that there are sort of branches off of it, right? If my PhD thesis was about finite element analysis, but I also was interested in fluid simulation, other topics in computer graphics. And so, that's kind of the difference between the two experiences. You have this broad base as an undergraduate, and then as a grad student, you really go deep into something. I think that's pretty typical for a lot of people who go through that path.
Yeah. Could you actually dive a little bit deeper into what your PhD research was about?
Sure. So in computer graphics, you get, most people think of computer graphics like, oh, you draw a picture, right? Your computer takes some data in and it outputs a picture, like a frame of a Pixar movie, for example. But in computer graphics, we also care about not just a single image, but how do I generate an animation, right? If I want to generate an animation of something, I need to know how things move. Now, for some things, that's easy. Like for a person, if I want to put a person in animation, I can use what's called motion capture. I put markers on the person and I put a bunch of cameras in the room. The cameras track where the markers move. And now I can use that data to animate a figure of the person, to animate a character. But if you want something like clothing, which kind of moves around and flops about, kind of has this complicated motions, maybe not my shirt so much, but like think about a big cape, like Batman's cape. It moves all kinds of interesting ways. Or if you want a movie that's going to have water in it, where it's going to splash or a waterfall or whatever it's doing. Or in the case of the finite element stuff I was doing, you maybe want to like take a building and blow it up. Like you've got a movie, the aliens come and they blow up some building with their space lasers or whatever, right? How do you generate the movement and behavior of those things that you can then render the images for and use it for a special effect in a film, use it for, like in a Pixar movie where it's the whole film's animated. And there's a lot of ways that early on in the field where like ad hoc things were done. Like, people look at the ocean and say, well, I can just make some sinusoids. That looks like ocean waves. But very quickly, when you try these sort of ad hoc approaches, you see that there are limits to what they're able to do. And what turns out to work really well is to say, well, wait a minute, if I want to model a building, collapsing when it's hit by a laser from an alien spaceship, well, maybe I should actually model the physics of how a building, that structure works. And when it's damaged, it'll, naturally, because you're modeling the physics of how it behaves, it'll collapse and do whatever it's supposed to do. And so that's where you take these methods like finite element analysis, which is traditionally used like in engineering. Like if I'm designing a car, I might use finite element analysis to see whether or not my frame is strong enough to stand up to a collision, protect the people inside. But I can also take that same car simulation built using a finite element method or whatever method I like. And I can say, well, I want to make a movie or a video game, and I want my car to smash into something and get crunched up. And I don't really feel like going out and buying a real car and smashing it into a wall just to get that part of the movie. So I can use the simulation to do it. I don't need to blow up a real building or a scale model or something to get my special effect in whatever movie. I can use a simulation to do it. And so that's what my PhD thesis was about, taking finite element simulation, in particular for doing crack propagation through brittle materials, and saying, all right, can we use this to do special effects in film? And so that was what my PhD thesis was about. And actually, after I graduated, we took that, I teamed up with some other friends and we started this little company, Pixelux, where we actually built software that took that technique that I developed and turned it into something that animators could actually use. It's been used in about 200 films at this point. And so that was also a nice thing, right? Taking that research that was my PhD thesis and actually turning it into something that was usable by a lot of people for doing animation.
Yeah. Are there any films you'd like to name?
There's a lot of them. I guess the two first films were the first Avatar movie and a movie called Sucker Punch. The first Avatar movie didn't use it too much. I don't know if you've seen the movie, but there were these kind of like like flying helicopter like vehicles they have, and there's some combat scenes where like there's the flying helicopter things on one side and like these giant pterodactyl things on the other side, and they're like fighting with each other. And so there are a lot of scenes where the mechanical helicopter things get smashed apart, and that smashing apart was animated using our software. The movie Sucker Punch wasn't as popular as the Avatar movie. It's a Jack Snyder movie. I thought it was pretty good, but it doesn't have a happy ending, right? I won't spoil it, but it's not a happy ending, and so it's not really the kind of movie that people flock to the theater to see. It actually didn't do very well in the box office. But I love that movie because they took our software and they used it in amazing ways that you can build a tool, but when you put the tool in the hand of an actual artist who knows what they're doing with it, that's when you see what it's really capable of. And when I watched the movie Sucker Punch, and there's a giant temple that collapses, there's some trains and ships that get blown up, there's inside this temple, this giant robot comes in and shoots a bunch of things. Like all those scenes were done using our software, and it was just amazing to look at what somebody, a bunch of talented people. It was the effects were done at MPC, Moving Picture Company. It's a special effects house in Vancouver, and it was just really amazing to see what they were able to do. The technical stuff we did, the technology of it, but then they use it to create something. It's sort of like if you came up with you designed a paintbrush. Well, that's nice. You hand it to an artist, and suddenly you see what it can really do.
Yeah. So after you did your PhD, what jobs did you hold between then and becoming a professor?
Zero. So
Zero.
I went directly from my PhD to starting as a professor at UC Berkeley. Um, as I was while I was in my PhD, I worked at I had a period of time where I wasn't working at Georgia Tech. I was working at Microsoft. So I had other jobs, but it wasn't like I finished the PhD and then did something and then went to the faculty position. By the time I finished my PhD, I had enough experience, and they hired me to be a professor at UC Berkeley. Um, and I'm still there. That was back in 2000, so I've been there for I guess 25 years, of just about. Um, but throughout that time, I've also, at the University of California, which Berkeley is one of the campuses, we're given 1 day a week to pursue outside activities, right? And that could be starting your own company. It could be going to work somewhere. You have to make sure there's no conflicts with your job at the university, but as long as there aren't, you have that freedom to do other things. And typically, what people do is they take their research, they take the ideas that they're studying, and they find ways to apply that out in industry. So Pixellux, that company that I started after I graduated, after I started my PhD, that was an example of one of those companies, right? That was something we did outside the university. We built a commercial tool. Been involved in several companies over the years, that most of them focusing on simulation. I guess one of the other big ones was a company called Avometric, where what we did is, again, using finite element simulation. But in that case, we built a model for modeling clothing, very realistic, very accurately. And we kind of originally thought we were going to do that for special effects and film again. But what we realized was there were easy to use tools for doing special effects. And the tool we had built had a level of accuracy and precision that was different than those other tools. But you don't need that accuracy and precision for special effects. What you do need it for is if you're a designer and you want to see, like if you're a clothing designer, everything you're working with is 2D. It's 2D pieces of cloth that you sew together, and then it turns into a shirt, right? But you don't know what it's going to look like until you actually sew it together and put it on somebody and see how it hangs on their body, right? You can't really see what it looks like when it's just 2D patterns. And the problem, if you're a clothing designer, is that, well, cutting it out, stitching it together, and putting on a body is a lot of work. Maybe, and also not every clothing designer has the skills needed to sew up a garment. And so a lot of times that means that your design loop, your iteration loop, when you make a change to your design, you want to see what it looks like. Well, it's very slow. You have to wait now a whole day while somebody else in your company sews everything together and gives it back to you. You can put it on your model and see what it looks like. Or if you're working at a smaller company, you might not even have that person in company, and you have to send your design out to somebody else. They work on it and they FedEx it to you. And now it took 3 days before you saw what your change did. That's not really an easy way to design things. And so what we did is we said, well, if we can simulate the physics of how clothing moves, how cloth behaves, we can take that pattern and we can turn it into a simulation, and we can show you what it will look like in simulation 30 seconds, right? You push a button, 30 seconds later, you see what it's going to look like instead of waiting 2 days. And so we built the SOT. So we decided to give up on the idea of using it for special effects. We pivoted towards doing it for clothing design. And eventually we ended up selling the company to, there's several companies that are called Gerber, right? There's the baby food company, there's a Gerber Knives. There's also a company called Gerber Technologies that many people haven't heard of, but the big machines that cut the fabric in clothing factories, that they make those. And they also make a piece of software that's used for designing clothing to be manufactured on those devices. Something like 30% of the clothing in the US is manufactured on their devices using their software. And they purchased our company to take the simulation we built and integrate it into their design software. So chances are, I can see you wearing a t-shirt, but I don't know what else. But chances are that each of us is probably wearing 1 or 2 items that probably have been designed using that software. 30% of clothing.
So actually going back a little bit, I wanted to first ask you what motivated you to go into academia and become a professor?
That's a good question. I think at first, I think I was a little bit, let's try this and see how it works, right? When you get your PhD, well, you can go do a postdoc. A lot of people do, but whether it's when you finish your PhD, when you finish your postdoc, you've done a bunch of academic work. You've got some publications that papers that you've written and published, and that's a good time to apply for faculty jobs. If you go out and work in industry, then what tends to happen is you work for a while, but you're not public, in industry, like if you go work for Apple, you don't write papers about what you're doing. You do the work and it shows up in an iPhone, right? But you don't write papers about it. Which makes it very hard to go from industry into academia. There are exceptions, like somebody who's become, sort of a leader in their field in industry might, find a position in academia, but generally it's hard to go that way. It's a lot easier to go the other direction from academia into industry. And so my thinking was, well, I might like academia, I might not. I might like working at some company, I might not. So let me try the one that is sort of, it's a one-way valve. So let me go try this side first. And then if I don't like it, I can go through the valve into industry. But if I do it the other way, that won't really work. And what I found is I enjoy working in academia. I enjoy being a professor. Interacting with students is a lot of fun. And you can really get a lot of work done, right? The research that a professor does is primarily done through the hands of their students, right? You advise, I have PhD students, I advise them on how to, they have a problem, I give them advice as an advisor. But the actual research is their fingers on the keyboard typically. And that means that from my perspective, I'm able to get a lot done because if I do something myself and I do all the work myself, I can kind of do one thing at a time. But when you're working with a group of students, now there's 10 things you can do all at once because you're working with a team. And I really enjoy that. It's great. I also like, the experience working in industry. It's kind of the same thing, right? You go and say you're going to build some software, you hire some people, and now you've got a team working on something. In academia, there's a lot of freedom. You don't have to necessarily worry about something being a product. You can do it just because it's interesting. And maybe it turns into a product, maybe it doesn't, maybe it doesn't ever make anyone any money. It's just interesting. And so I kind of like that freedom. At the same time, I also like it when you have the pressure of trying to build something that's actually going to work, that people are going to use it. So I think both are great. And I guess one of the things that's kind of nice is that when you're in academia, most universities give you some time to work on outside the university. So you kind of get the best of both. And it can go the other way. I have friends who have been working in industry for a long time, and they might have an adjunct appointment at a university where they maybe teach a class about the kind of stuff that they did in their industrial career. They might also teach about that. So I guess you can go both ways, but I think that, generally speaking, it's easier to go from the university and then do the industry stuff on the side. At least that's where I ended up, and it's been good so far.
Yeah. So what is your research currently about?
So a couple of different things. One, AI is something, I'm sure, unless you live under a rock out in the middle of the Pacific on a deserted island, you've heard about all the big changes that are happening because of artificial intelligence. It's really a particular branch of AI, which is called machine learning, which is basically training, building systems that have parameters, and those parameters, rather than a human deciding what they should be, you basically give the program a goal, and it optimizes the parameters to let it do something. An example of that is like if I want to tell the difference between a cat and a dog, photograph of a cat and a dog, I don't know how to do that. I mean, I know how to do it myself, but if I tried to explain it to you, I'm not really sure what I would tell you. I mean, this looks like a cat, this looks like a dog. I don't know what to tell you. And so if I try to write a program to do it, I don't know what to do. But what I can do is I can write a program that takes an image, it does some processing on it, and that processing has parameters, and you now show it lots of examples. And when it gets it right, the parameters that were responsible for getting it right, you increase those, and the parameters that were wrong, you decrease those. And when it gets it wrong, you do the opposite. You keep doing this over millions of examples, and eventually you have a little neural network, or a little piece of code that can tell you the difference between a cat and a dog. Nobody actually knows how it really works, but there you go. And so one of the things that I'm interested in right now is looking at how this new technology that's really blossoming can be used to do things that, apply to existing problems. So right now, one project is looking at doing simulation of physical systems. In this case, looking at designing like a microwave antenna, or like the antenna on your cell phone, right? That design, it's got to fit inside a small package, and you want it to be a very sensitive, good antenna. And so the way that works is people will do a simulation of the antenna, and see how it works, and they'll adjust the design and simulate it again, sort of like the clothing, but instead of looking at clothing on a hanging on a body, you're looking at how well the antenna performed in simulation. And traditionally, those simulations would use things like grids, traditional methods. But now we're looking at how we can use AI to solve those same problems. And it's kind of super interesting because we can use these machine learning techniques both to solve the problem directly, but we can also then take lots and lots of solutions and then train the model to understand what parameters are going to create good solutions and what will create bad ones. And we can actually design new methods that way. It's kind of a new branch of both AI and simulation where the two are coming together. Super interesting. And so that's one of the things. There's also other stuff that's not really about simulation, but sort of, again, looking at how artificial intelligence, for example, can be applied in the field of virtual reality. Are you familiar with the game Beat Saber?
Yeah.
Yeah, the notes come at you. You have a little pair of virtual swords, and you hit the notes as they come by. Well, one question that I had a student that Vivek Nair that was he was interested in looking at, could the motion of your head and hands when you're using a VR headset, so you're holding controllers, you got a thing on your head, they all have trackers. And what he wanted to look at was, can you use this to identify who the person is, right? We all move in unique ways. And you probably notice this, like if you're walking down the street and you see someone really far away where you can't really identify them, but you might recognize it as your friend or family member because of how they move. It looks familiar, right? And so that's a pretty common experience. And there's even studies like, back in the 70s where they would show people just like dots of movement. And people would say, oh, that's this person. They'd recognize who the person was just from how the dots moved. So we thought, well, can you do that with this, with the head and hand trackers from a VR system? And to do this kind of thing, you need a lot of data. And the old way of doing things is that you would have got a bunch of people to come in the lab, put on the thing, record them, and then they leave. And maybe if you put a lot of effort into it, you might get like 100 people to come through and give you 5 minutes each, right? That's a lot of effort. Well, it turns out this game Beat Saber, there's a third-party leaderboard system. So when you play the game, if you're interested in, you install the mod for the leaderboard system, and now your score gets uploaded to leaderboard system. You can see how you're doing compared to other people. But of course, people take it seriously, so they don't want people to cheat. So to avoid cheating, what they do is when you upload your score, it also uploads a recording of your head motion and your hand motion. So that somebody can look at it and verify, okay, this person actually played and got that score, as opposed to they just uploaded a number that was good. Cheating. Well, the thing about that's kind of cool is that leaderboard system has over 100,000 people using it. And each one of them has on average uploaded maybe 3 or 4 hours of playing, right? Because you play a lot, you play one song, you play another, they're all getting uploaded. And we realized that was an amazing piece of source of data for doing some experiments to try to understand this problem. So we contacted the people that ran the leaderboard system and told them what we wanted to do, which was we wanted to use their data to investigate this hypothesis, this thesis. Can you recognize people from their VR motion? They thought this was interesting because, there's obviously privacy implications, right? If I can do that, then you need to know about it so that, you can protect people's privacy, right? For example, let's imagine instead of doing this thing over over Zoom, we did it in VR. Like, if you've probably seen, we could put on headsets and now we're in a VR world and we talk to each other and stuff. Well, you could record my motion because you need it, right? Because your computer has to animate me to show you my avatar. So you've got my motion at your machine. You record it. I don't know you did this. You just recorded it quietly. Now, after we get off the call, maybe I go play some video games. And maybe in those video games, maybe I don't act very mature, not very professorally. I shout at people and say, "Hey, you suck," or whatever. Just imagine bad behavior in a video game, right? You're blowing off steam. Well, I probably don't want that associated with my professional identity, right? But if you've recorded my motion and you now get a group of people to go into these games and record motion from other people, and there's a way to compare them, now you know who it is. It's sort of like if every time you went on, like, I don't know, Reddit or wherever you like to go online, you had to sign with your sign your message with your real email address and a thumbprint, right? that would be sort of very chilling. You would maybe not feel very comfortable expressing yourself online in that situation. So we said, okay, well, let's investigate this. The people running the leaderboard system gave us a copy. They sent us a drive with a copy of the data on it. It was a lot of data, like a terabyte or something, a couple terabytes. And what we found out was that your motion is indeed very identifiable. If you let me record you moving around for about 90 seconds, I can identify you more accurately than a fingerprint. So that's something that's actually kind of concerning. We did some follow-on work where what we did is we took, and by the way, the way we do the identification is we trained a network to do it, trained a neural network, an AI system to do it. And we said, all right, well, we're able to do that. Well, that's kind of scary. Can we now find a way to like give you a voice changer? You know how like those voice changers you see in movies where the person talks and it sounds like a robot. You can hear what they're saying, but you can't identify who the voice is, right? Like the kidnapper says, hey, leave the money over here, but the police can't identify the voice because they use the voice changer. Well, can we make a voice changer, but for your motion? And so we actually built a system, trained it, got it working. Eventually, we published this just a little while ago. And so we were able to build a system that would take your motion and preserve the overall semantics. That is, if you're playing a video game and like I hand you something, or I pick up something off the ground, or I'm just walking, all that still is, you're still walking, you're still handing people something, but the details that make it look like you and not somebody else have been removed. Just like if you use a voice changer, you're still saying whatever you said, but the details that made it recognizable as your voice as opposed to someone else's have been removed. And so the idea is that this kind of software can now give people anonymity in VR environments, right? You get to control whether or not, you don't have to tell it, advertise to everybody who you are. You're not like putting your thumbprint on everything you do. You can go online. I mean, it's not like you're totally anonymous. If you create an account to go join something, you still create an account so the people running the servers know who you are, but the other players don't have, if you play Call of Duty, the other players don't need to know your home address, right?
Yeah.
So those are a couple topics. I mean, yeah.
Yeah. So moving on, since you're a professor, I wanted to ask you, what programs does your university offer that could benefit incoming students who want to go into a field that you work in?
Well, we have a very good CS program. So I mean, you see me like after they're admitted or before they're admitted, like when they're high school,
Or once they're admitted.
Yeah. So yeah, I mean, we have our program, and it starts off with some intro level classes and gets progressively more difficult. We do have there are lots of resources to help students. We have student-led groups. We even have classes that are taught by students. We call them decals. Cal being UC Berkeley Cal, and decal. So it's not taught by a professor. These are classes that are taught by students, and a lot of times they'll be on special interest topics. Like for example, actually, one of the decals we have is on video game design. So we don't teach an actual class on designing video games. We teach you how to program. We teach you lots of computer science stuff. But if you actually want to learn how to use Unity and make a video game, or Unreal and make a video game, well, that's kind of a more hands-on applied thing. And so we have a student taught decal that is on game design. It's a series of lessons that the students do on basically learning to use Unity to design a simple video game. I'm the faculty advisor for that decal, and we've got hundreds of other ones at campus. We also put a lot of information, even before you come to get admitted to your undergrad, wherever that is, Berkeley or anywhere. We also have a lot of material online related to our classes that's available to anybody. It's available to you if you wanted to. So this is publicly available information that is about our classes. You can see the syllabus, the assignments. A lot of the professors will make explanatory information, sort of like we're making a video right now, but maybe we could have one where I would go into details about, some particular topic. And I'm sure you've seen videos like that online. There's lots of ones where somebody will explain something at a level that's intended to be accessible to high school students or general audiences. So we have a lot of, there are a lot of resources like that. It's a big school. And then I think that, just broadly speaking, there's a lot of resources out on the internet. Like if you're interested in learning about AI, you can certainly learn a lot in our classes, but there's a ton of information out there from tutorials to people recording their own lectures and putting them online. There's a lot of information if people want to learn stuff.
Yeah. Aside from decals, are there any particular clubs you're interested in, whether they're academic or non-academic?
Um, there's some other clubs on campus. There's like a VR club. There's actually two of them. There's one where it's actually being supervised by another professor, Alan Yang, where they're actually like building an open source VR headset. Right. That's their objective. They want to. So they're if you think about a VR headset, it's got all these components, right? And when Meta designs it, they design each component custom for their thing, and they sell it. But you can't change it. If you decide you want to do something different, you can't open up your headset and just modify it. It's closed. It's closed source, right? Both in terms of software and hardware. Uh, so this group is they put together. They basically designed a headset using commercially available things you can just go online and buy, components, software. So design that goes together, software that can be used to run the thing, and that's one of the clubs here at Berkeley, doing some kind of cool stuff. Yeah. So, and to be honest, there's probably dozens of clubs that are pretty cool that I don't know anything about, right? It's a huge campus. And so really you can't keep track of everything. But yeah.
Yeah. And then for my final question, I wanted to ask what your biggest piece of advice would be for an undergrad coming into UC Berkeley.
Well, one big piece of advice is what I right at the beginning of this I mentioned, which is this trilogy of finding something you like to do so that you can enjoy it and be good at it, that other people care about, and that is not that is difficult, that you're special in your ability to do it. So that's one general thing, but also a lot of people come into and they forget about the part about liking it. Like so, it's not too uncommon to see people come into our CS major and they don't actually like programming. Well, why'd you pick this as a major? Well, I wanted to make money. I wanted to get a good job. And I don't fault anyone for wanting to get a good job. Everyone wants a good job, right? But if you study something just to get the good job and you don't like it, I think you're setting yourself up for unhappiness. And I've seen lots of students that, their parents tell them something, and I'm not saying you shouldn't listen to your parents or you should ignore them, but, don't just do something because other people tell you to do it. You need to think about yourself and, what do you enjoy doing? What motivates you, right? Because if you ignore that, then you're just gonna be always forcing yourself to do things. You really want to find something that's important to you, that you enjoy, and that you're willing to put hundreds of hours into, right? At the same time, sometimes students will show up and they'll just not really have a clear plan about what they wanted to do after they graduate, and they kind of just wander around taking classes, maybe changing their major a couple of times, and then they finally graduate with some random major. And I don't, I guess there's nothing inherently wrong with that, but I do think that students are better served by thinking ahead. And it's kind of like the further ahead you think about what you want to do, the more time you have to plan and the easier it is to put things into place, right? So if you are in undergraduate and you want to go to grad school, well, make that decision and then say, okay, well, what do I need to do as an undergrad to get into grad school? Well, I should get involved in a research lab as an undergraduate researcher, maybe try to get involved in something that leads to a publication, because that's what's going to help you get into grad school. On the other hand, if you're like, I want to graduate and go into industry, well, working in a research lab maybe isn't that, it's cool, but maybe you're better served by doing a good internship at a company similar to the one where you might want to get a job afterwards. You'll see what it's like to work at that place, see what this kind of work is actually like. So you'll get a chance to see if you like it or not. And also it looks good on your resume when if I'm going to hire somebody to do X and I see that they already have an internship where they did X, I say, okay, great. This person knows what they're doing. You also, some students, they don't want to go into academia. They don't want to work for anyone else. They want to start their own company. Well, if that's what you want to do, think about it and make that decision. And then think about, what do I need to do to make that happen, right? Sure, you need to take maybe if you want to start a company doing some CS technical thing, you need to learn that technical stuff. But maybe since you decided that that's what you want to do, you now know I should also maybe take some classes over in that business school. Right? Maybe I should also develop cultivate some relationships with those professors who might be able to help me raise funding when I go start my company, right? By deciding what you want to do, you can always change your mind, but by deciding what you want to do and having a goal, you're able to plan towards that goal. If you just show up and say, I'm here to just have a good experience, you'll have a good experience. That's great, but you won't. When it's over, you won't know where you're going. You won't be planned. You won't be set up to go in that direction. So I think students are really well served by thinking ahead about what it is they want to do. Not just tomorrow, not just next year, but even when you graduate 4 years from now, what do you want to be doing? You're not locked in. You can change your mind. It's not something to stress about. But when you think ahead, you find it lets you know which opportunities you should be looking for. It lets you know how you should plan things. When you have a choice in front of you, you can think about it in terms of how does it, which direction gets you towards your eventual goal. So I think that's a big thing that a lot of students don't do. They show up at school and they say, okay, I'm here. I'm not going to think about what happens after until I'm a senior. By that point, it's not too late. But things you could have done early that would have helped you, like if you want to get involved in a research lab, well, you can't do that your last semester of a senior year. If you want to go get an internship, well, you can't do that your last semester of senior year, right? It's too late. You need to do that during the summer or whatever. So yeah, that'd be one of the big pieces of advice. Think about what you want to do, make a plan. You can change your plan, but make that plan and use it to inform your decisions.
All right, then. Thank you for joining me.
Yeah, it's my pleasure. Thanks for having me on your podcast.